explicit by knowing what we mean by non-parametric.
طيب, could you please go to the first formulation?
Sure. Yes.
Yeah. يعني I didn't get the constraint يعني حاولت بس ما عرفته.
Okay. The easiest one is the first and second one, and if you understand these two, you will understand these two. So for this one, if you look at it, you see that xij, you'll see that the constraint is over ij and k, and xij and xik. So I here is the same one here, which means that they are on the same row, because the position is known by row and column. Okay? So having the same value here means that we are talking about columns for the same row. So that means that if we have the same row, let's say that I is here. Okay? Now j and k can be will be the columns. Yes. Okay. So if you put any two columns for the same row, we should not have two queens on the same row, right? Because if that's the case, they will attack each other. That's why the possible values will be 0, 0, 0, 1, 1, 0. But you don't see a 1, 1 here, because that's violation of the constraint. And the same for the others. Okay?
Yeah, thank you.
Okay. Ghanem again. Ghanem, you have a question?
Yes. In the second one, I mean actually in this one here, the domain is 0 and 1.
Yes.
Means either in that position there is a queen or no queen.
Exactly.
Okay. So in formulation, the domain changed to 1, 2, and 3. Although our variable is a row.
Yes.
And we're using actually the variable as a way to,
I take that.
it's actually part of how to find the answer.
Yes, exactly.
Number 2.
So my point is,
Evil shield here.
technically, because of how the rules of this exercise is, each row can only have either one queen or no queen.
No, it cannot have no queens. It has to be one and only one queen.
Okay. Well, I mean, yeah. Well, okay, that makes sense. But my point here is the domain 1, 2, 3, 2, all the way to n, which is not possible.
No, n is the size of the board, right? N times n by n. So n here is the column in each row. So for example, if Q1 is 2, that means that I will put the queen at the second column of the first row, because I want to determine where exactly that row the queen will be. So it can be in the first column, in the second column, in the third column, in the nth column. Okay? That's why the domain.
You mean like the domain is actually the column?
Exactly. Yes.
Okay, yeah, that makes sense.
Okay.
The other one, the domain was used not as.
Yeah, it was just binary. Yes, because we had the variables everywhere.
Yeah, that's why I thought that because we're using Q and not row. I thought this was about queens, and then the domain is how number of queens exist. That's why I got mixed up.
No. It's not the number of queens. It's the column number.
Thank you very much.
Sure. Okay. Hamza, did you have a question? Hamza Saleh? Salah? Okay. مش مشكلة ولا you got the answer? Okay, good. Okay, now let's talk about. Okay, no problem. Let's talk about how to start to think about solving CSPs. So we'll talk about the concept called constraint graph. So what is a constraint graph? Let's first define what we mean by binary CSP. In binary CSP, each constraint relates at most two variables. So for math coloring, you saw that the constraint, every two states have to have different colors, right? So the condition here of the constraint relates two variables only. If we have a problem where all the constraints relate 2 variables at most, then this is called binary CSP. Okay? Notice that the constraint might relate one variable only. And for example, if I told you that, okay, with map coloring, I want to map empty Muslim territory with blue. So that's now a condition on one variable. Okay, that's a condition on one variable. That's okay if I have the constraints up to 2 variables, relate up to 2 variables, then this is called binary CSP. Now, for binary CSP, we have what we call binary constraint graph. So we have a graph where the nodes are the variables and the edges are the constraints. For example, like this. So this is exactly the map coloring problem, where every node here is a variable, and the edges are constraints between the variables. So there is a constraint between NT and WA, there is a constraint between NT and SA, there is a constraint between Q and SA, and so on. And if and of course for T, for Tasmania, we don't have any constraint, by the way, because it's far from the other states, so there's no conditions. So we don't have any edges coming to or from that variable. And all the constraints here are relate maximum to 2 variables, and this is why we call it binary constraint graph. But generally, the graph, by the way, can have constraint. The graph can have constraints that relate more than 2 variables, as we will see inshallah in the next example. But at that point, this is a binary constraint graph because the constraints relate at most 2 variables. The main concept here is that we put the nodes to be the variables and the edges to be the constraints. Now, this by itself doesn't tell us everything about the problem, because we have to know what exactly each constraint means. Okay, so we should have with every constraint the meaning of it. So, for example, in the map coloring problem, that means that the values of these 2 variables should not be equal. Maybe in other problem that might be less than or equal to, or something else. Okay, so it depends on the problem. But eventually, generally, in the graph there will be an edge that represents a constraint. With the constraint, there must be some information about the meaning of that constraint. Now, why is that a problem? First, why is that important, the constraint graph? First, this is a way of formulating the problem, is for visualizing the problem. Second, we will see inshallah later in the next lecture probably, or the lecture after, how the graph can be used actually, or the structure of the graph can be used to solve the problem. For example, Tasmania here has no edges to the other states or the other variables. That means that it is completely separate from the other part of the problem, which means that we can solve it completely separately. Okay, so that's just an example of something that the graph structure can tell us about the CSP. Questions? Hamza?
Yes, sir. Is it the constraint graph similar to the bipartite graph that you can color each node?
No, the bipartite graph is a very special case where we have 2 sets of nodes. Here we don't have this. It's just that the edges relate to variables with each other. Okay, and actually we can even have, as we will see inshallah very soon now in the next slide, that the constraints can relate more than 2 variables generally. Okay, now let's move to the next example. Now, in this example, the problem is called crypto arithmetic problem. This problem is a really nice, funny problem, where we want to write the arithmetic operations with letters, but still every letter should have a value. So, for example, I want to write something like 2 plus 2, and I get 4, where every letter here has a value that is valid arithmetically, mathematically. Okay, so I want to assign a value to O and a value to W, the value to T, so that when I write 2, but now as in letters, it will be interpreted as a number, plus 2, I will get 4, where also the values of 4, when I assign value to every letter here, it will be actually the correct answer to this operation. Okay, so the variables here are, or should be, the letters. So I should have a value for F for O, a value for W, because value here is digit. So I have to assign a digit to every letter here. To O, to W, to T, to F, to U, to R. And not only that, because you know in mathematics, when we add two numbers, we might have a carry here, right? So O plus O is not equal to R only, it will be equal to R plus 10 times the carry. So we will assume that there is a carry here called x1, there is a carry here called x2, and there is a carry here called x3 out of these operations. So the variables here will be F, T, U, W, R, O plus the 3 carries, x1, x2, x3. Okay, and for that simple example, we'll just focus on this one only. We don't have 1 plus 1 and 1 plus 3 and all of that. We just for simplification, we only have this now. Okay, 2 plus 2 equals 4. Now the domains will be the digits 0 to 9. Okay, so every value here, every letter here will have a value from the domain, because it will be eventually it will be addition. Now, what are the constraints? The constraints will be the conditions here, the equations. So first, we have a constraint here that says that every letter here, every different letter, will have different value. Okay, so that's a constraint or a condition in here in the problem itself, is to assign a value to every letter that is different from the other letters. This is what we mean by all diff here. Of course, this is an implicit constraint. Another constraint that's also implicit is the equation for the first operation here. O plus O equals R plus 10 times x1. Okay, and we can say also W, of course, x1 plus W plus W equals U plus 10 x2, and so on. So we can write all the mathematical equations here that will make this possible. Now, the constraint graph, you see that some constraints don't relate only to variables. So, for example, this constraint relates O with R with x1. So how can we represent that in a constraint graph? Let's see. O, R, and x1 are related by that constraint. So if the constraint is relating more than two variables, we draw it as a square, and out of that square there is a line or edge to every variable. Okay, so this is now n-way constraint that relates O with R with x1, which is actually this equation. For another example is that constraint or diff, which relates all of these variables together, and this is the one. Okay, there is a square here, and then there is an edge to every variable in that constraint, and so on. So this is now a constraint graph. That's no longer a binary constraint graph, because there are some constraints that relate more than two variables. But still, this is a constraint graph for this problem. Okay, any question about this? So that's another example of a constraint graph. Hamza?
I'm failing to link this to what we're just doing. I get this problem, but is this just an example of a problem, or is this?
Yes, of course. This is an example of the problem that has nothing to do with map coloring.
Oh, okay.
Any other questions? But here, this is just an example of a constraint graph that is not binary. That's a clear example of a non-binary constraint. Okay, let's move on and let's think about varieties of CSPs and constraints. So, in terms of variables, we can have generally in CSP, we can have discrete variables that have finite domains or infinite domains. In case of finite domains, the domain D, the domain will be of size D, which means that every variable can have value of D possible values. So D times D, that will be order of D to the power n assignments or possible assignments to the variable. In case of infinite domains, we can have a domain like integers or strings. For example, variables are taking fixed start and end times each job. I'm scheduling jobs and I can start at only at specific times, hours, for example, but in a very long time. Okay, so it's kind of infinite domains, but still discrete. I can also have continuous variables where, for example, here the variables can be the start and end times that are not fixed. I can start at any time, I can end at any time. So that's an example of continuous variables. In terms of constraints, we saw that some constraints are unary, which means that they relate only one variable, like saying SA is not equal to green, or binary when we relate two variables, SA is not equal to WA, or higher order constraints as we saw in the crypto arithmetic problem. We can also have what we call soft constraints. So for example, I can say for map coloring problem, it's better to have red for Tasmania than green. So that's a preference. We call it soft constraint. It's not a must to have red, but it's better. And usually we represent that by a cost, given a cost for every variable. And the cost will be less if we maintain the preference. Okay, it's like priorities, but still they are not hard constraints.